So notice that if A and B are both square matrices of order n, and their product, A times B, is singular, then at least one of the factors, A and B, is singular, since otherwise there exists the inverse of A and the inverse of B in the set of square matrices of order n, such that the inverse of the product is the product of the inverses in reverse order. Now we can extend this theorem to any arbitrary product, and we will prove it for a finite product as a corollary. So let A sub 1 through A sub r be square matrices of order n if each matrix A sub I, for I in the range from 1 to r, is invertible, then the product A sub 1 times A sub 2 and so on through A sub r is invertible. And in fact, the inverse of the product is the product of the inverses in reverse order. So proof. Since A sub 1 and A sub 2 are invertible by the previous theorem, the product A sub 1 times A sub 2 is invertible, and the inverse of this product is the product of the inverses in reverse order. So now suppose that the product A sub 1 through A sub k for k greater than 2 and less than r is invertible, and that the inverse of the product is the product of the inverses in reverse order. Then, since the product A sub 1 through A sub k and the matrix A sub k, A sub k plus 1, are invertible, by the previous theorem, we have that the product, the matrix A sub 1 through A sub k times the matrix A sub k plus 1 is invertible, And in fact, the inverse of this product is the product of the inverses in reverse order. So we have the matrix a sub k plus 1 inverse times the inverse of the product a sub 1 through a sub k, where the inverse of the product a sub 1 through a sub k is the product of the inverses in reverse order. And hence, by induction, the product a sub 1 through a sub r is invertible. And in fact, the inverse of the product is the product of the inverses in reverse order. So next we will show that the inverse of a square matrix is unique if it exists. So let A be a square matrix of order n. Then the inverse of A is unique if it exists. So proof. Suppose that the square matrices B and C are both inverses of the matrix A. Then, since B is the inverse of A, we have that B times A is the identity matrix. And so if we post multiply both sides by C, we have that the product B times A times C is the identity times C, which is the matrix C. Now, since the matrix C is the inverse of A, we have that A times C is the identity. And so if we pre-multiply both sides by the matrix B, we have that the product B times A times C is B times the identity, which is the matrix B. And hence, the matrix B is the product B times A times C, which is the same as the matrix C. That is, B and C are the same matrix, and so a square matrix has a unique inverse if it exists. So next we will show that the set of all invertible square matrices of order n, and for now with real entries, is a group under matrix multiplication and this group is called the general linear group of degree n and is denoted capital GL sub n over the field R, or capital GL, taking as an argument the degree n and the field R. So proof, we'll start with the most obvious property. For every matrix in this set, there exists the inverse of the matrix A in this set, since once again this is the set of all invertible square matrices of order n with real entries, such that A times A inverse is the same as A inverse times A, which is the identity matrix. Further, the identity matrix is in this set, since the identity matrix is its own inverse. And so there exists the identity matrix in this set, such that for every matrix A in this set, we have that A times the identity is the same as the identity times A, which is the matrix A. Now let A and B be two matrices in this set. Then since A and B are both square matrices of order n, the product A times B is also a square matrix of order n. And since A and B are both invertible, the product A times B is invertible. And so the product A times B is once again an element in this set. Now let A, B, and C be three matrices in this set. Then since A, B, and C are square matrices of order n, they are conformal, and so their product is defined. And we have already demonstrated that for conformal matrices, A times the quantity B times C is the same as the quantity A times B times the matrix C. And therefore the general linear group of degree n with row entries is a group under matrix multiplication. So notice that the general linear group of degree n is not abelian for n greater than or equal to 2. In the case n equals 1, we have the degenerate 1 by 1 matrices that are invertible. This is the set of all non-zero real numbers. And so in the degenerate case, n equals 1, we have the group of non-zero real numbers under normal multiplication. But for n greater than or equal to 2, the general linear group of degree n with real entries is not a Boolean. So as a third exercise, show that the set of all square matrices of order n with real entries is a monoid, but is not a group under matrix multiplication. Okay, so we will end here for today. Next time we will continue to look at the inverses of matrices, in particular how to compute them. So I hope you have enjoyed the 8th lecture. Thanks for watching.